Hello everybody and welcome to our video on asymptotes of rational functions. This is part 3. I'm just going to walk you through a couple of examples. So we're going to look at example A here, x minus 7 over x plus 5. We need to find all of the asymptotes. So first we're going to look for vertical asymptotes or point discontinuities, which is a fancy name for holes. We notice that this is already in factored form, and so if x equals negative 5, the denominator would be 0. Okay. So we know that there's going to be a discontinuity there. And the type of discontinuity, well, if we plug in negative 5 to the numerator and the denominator, we get a number over 0, which implies a vertical asymptote when x equals negative 5. For the horizontal asymptote, we're going to find the limit as x approaches infinity of this expression. To evaluate a limit as x approaches infinity, we're going to factor out the highest power of x in the expression. So I'm going to factor out x. That's going to leave me with 1 minus 7 over x. And in the denominator, if I factor out x, it's going to leave me with 1 plus 5 over x. Those x's can cancel out, leaving me with this expression, 1 minus 7 over x and 1 plus 5 over x. And I can take the limit as x approaches infinity by imagining that if I plug infinity in here, it's not a number, but as I plug larger and larger numbers in here, 7 over a very large number is close to 0, and so is 5 over a very, very large number, which leaves me with the limit of 1 over 1, and therefore we have a horizontal asymptote when y equals 1. This makes sense with our guidelines for horizontal asymptotes because these both have the same degree. So the horizontal asymptote would happen when we divide the coefficient of the numerator by the coefficient of the denominator. And because we have a horizontal asymptote, we therefore have no oblique asymptote. I like you to state that just so that I know you've been thinking about it. Now, what if we have a more complicated example like this one? We're going to start by factoring the expression fully. When I factor the expression, I notice that there's a matching factor in the numerator and the denominator, which suggests that there's going to be a hole. And in fact, we see that when x is 1, the denominator will be 0, and if I plug in 1 to the numerator, I also get 0. So therefore, we have a point discontinuity, also known as a hole, when x equals 1. In fact, this graph looks like the graph of 2x plus 2x minus 3, but it has a hole just at the point where x equals 1. So it doesn't look like a traditional rational function. Rational function. To find a horizontal asymptote, we take the limit as x approaches infinity. We factor out x squared, the highest factor from the numerator and the highest factor from the denominator, okay, of x. And we see that as x approaches infinity, anything that's being divided by x will approach 0. So we can knock all of those factors out, or all of those terms out. That leaves me with the limit as x approaches infinity of 2x over 1. But the problem is, if I was to imagine x getting larger and larger and larger, this is never going to approach one particular value, and therefore the limit does not exist, and there's no horizontal asymptote. I should have guessed that because I noticed that the numerator has a degree that is 1 larger than the denominator, so there actually is an oblique asymptote. And I can find that oblique asymptote by dividing the denominator by the numerator. Or sorry, I should say the numerator divided by the denominator. When I do my long division here, I see that I get 0 remainders, and that's fine. The remainders don't really matter, but this quotient here tells me the equation of my oblique asymptote. Okay, thank you and have a great day.